Good morning, friends. Welcome to my physics platform, which is meant to promote convergence of physics lovers. Okay, today I'll be starting with first law of thermodynamics, and because this is a very uh, important law in physics in the sense that this law, along with Newton's laws, can explain the entire classical physics. So the entire classical physics can be explained by Newton's laws and the first law of thermodynamics, or the laws of thermodynamics, because the laws of thermodynamics are the classical laws. So along with these laws of thermodynamics, along with Newton's laws, can explain the entire classical physics. So how means these are the only two laws. There is this group of the laws of thermodynamics and Newton's laws, which can explain the entire classical physics. Well, then to understand the law, we will take a situation. This is the situation. Suppose there is a box and there is a gas inside the box. So now this gas is my system. Everything, the stuff inside the box is my system, and everything external to the box is the surrounding. So let us say that this is Earth, and this box is placed on Earth. Fine. Now the system, that is the gas which is inside the box, can interact with the surroundings either by exchanging heat with the surrounding, or by performing work on the surrounding, or maybe some work is performed by the surroundings on the system. Okay, so these are the two kind of energy interactions our system can undergo with its surroundings. Heat is energy in transit, so it can flow through the system boundary into the system or out of the system. Similarly, work is also energy in transit. It can flow into the system or out of the system. Okay, these are the two energy modes by virtue of which this system can exchange energy with the surroundings. Okay, now this heat, I am assuming that the heat is coming into the system and some work is performed by the surroundings on the system. So the total energy that enters this system is the gas, is W plus Q. W plus Q is the total energy which is entering into the system. This energy, where will this energy go? What the conservation of energy law says, it says that this energy will not be destroyed. So the energy that enters the system will be equal to the change in the total energy of the system. It appears to be quite intuitive, because it is the essence of conservation of energy principle, the conservation of energy law of conservation of energy. So actually first law of thermodynamics is a consequence of conservation of energy principle. Fine. Now this is the total energy which is entering the system, which will be equal to delta E. Delta means change, E means total energy of the system. These are the notations that we will be following in understanding the law. Now E stands for the total energy of the system. I will talk about this later. Okay. Now some people also write it like this, delta W, and this actually I would like to emphasize upon here is, now what is W? W is the work which is performed on the system by the surroundings. So I would, if you like, you can emphasize it like this. This is W on, this is the work done on the system by the surroundings. Okay, some people write it delta W. Instead of W, they write delta W on, it becomes delta W on, plus delta, and instead of Q, they write delta Q. Now, I do not have any objection with these signs, because this is just a notation. But do not get confused that delta W doesn't mean W2 minus W1, and delta Q doesn't mean Q2 minus Q1. Here delta Q just means the heat which is being exchanged with the surroundings, and delta W means the work performed by the surroundings on the system. Delta W doesn't mean here that it is W2 minus W1. But these are just the notations. So fine, we'll follow this notation. there is no problem. Or we can follow this notation also, I don't have any problem, any hassles. Okay, now we talk about what is the meaning of this E, this symbol E. E means the total energy which is inside the system, the total energy content of the system. What is the total energy of the system? That is capital E. So that capital E will, suppose the box is at rest, so its center of mass, suppose center of mass is somewhere here, and center of mass is at rest, and then I would say that this box as an entire entity is at rest. But what happens if this box starts moving? Suppose the box is also moving, which is a general scenario in dealing with problems of physics, especially of physics. If the box starts moving, then the system as a whole is also moving now. So due to the movement of the system as a whole, there will be some kinetic energy associated with the movement of the center of mass. So I will call it, now suppose I want to know what is E, then E is equal to kinetic energy of the movement, kinetic energy of the system due to the movement of the center of mass. That is this factor. This factor will be half mvcm square. And capital M stands for the total mass of the system, and Vcm is the velocity of the center of mass of the system. Fine. So this is the energy possessed by the system due to the movement of the system as a whole. Suppose the box is at rest, then this part will be 0. Okay, now comes the other part of it, that is U, capital U. Capital U is the internal energy of the molecules of the system. So internal energy means the energy possessed by the molecules. And now this is a very complex scenario because the molecules are possessing energy in different modes. Suppose we have got diatomic, suppose this is a gas which is comprising diatomic molecules. Okay, now the physical picture of a diatomic molecule will be something like this. Now this is the physical picture of a diatomic molecule. Suppose it is a oxygen molecule, so it has got 2 atoms, and this is just kind of a dumbbell shaped molecule, just visualizing it like this and drawing a dumbbell. Dumbbell means this is a diatomic molecule, and suppose that its center of mass is somewhere here. So and this molecule is definitely moving inside because there is a lot of commotion, lot of chaos inside the system. Molecules are in a state of movement. Okay, now this is the center of mass of the molecule which is moving with some velocity v. So due to this movement, this molecule will have some translational kinetic energy, which will be half mvcm square, mv square, where m is the mass of the molecule. And there is also a possibility, because this is a diatomic molecule, it may be rotating. So suppose it is rotating with angular speed omega, then due to this angular velocity, it will have some rotational kinetic energy, which is half I omega square. And also there is a possibility of vibration. Now the molecule may be vibrating like this, and due to this vibrational movement, it will have some kinetic energy and some potential energy. Because if we are visualizing a spring here, because the molecules are interacting with each other, so the forces that they are applying on each other are quite akin to this spring force. So if we visualize that there is a spring here connecting the 2 molecules, so if the atoms are vibrating, then this potential energy of the spring is also changing. So the potential energy of the system is also changing. So this system also has got, this molecule also has some potential energy. Okay, now the picture is becoming very complex because this molecule has some translational kinetic energy owing to the movement of the center of mass. This molecule has some angular velocity, so it has got some rotational kinetic energy. As the atoms are vibrating, so it has got some vibrational kinetic energy and some potential energy due to vibration. And also this atoms, and if you go into the more deeply into the atoms and the situation of the atoms, then the atom is also having, let's suppose this is a picture of the atom. The atom has a nucleus. So the nucleus itself has got some nuclear energy, because inside the nucleus the protons and neutrons, they are interacting with each other, and due to that interaction there is some energy inside the nucleus. Plus there are electrons which are associated with the atom, which are also moving in some orbits, or which are also definitely moving inside. And so these electrons also have got some kinetic energy, and there is some interaction between the electrons, because electrons have negative charge and this protons or the nucleus has a positive charge. So there is some interaction between the two, and due to this interaction there is some energy of the system, that is some potential energy because of the interaction. So the system has got so many energy modes that it appears to be virtually impossible to calculate the energy of a single molecule, because you must have seen here that the picture is becoming very fuzzy now. So this means that it is almost impossible to calculate the energy of a single molecule, because this is also containing so many electrons, this atom, and if you take into consideration the total energy, then it will become rather impossible, because the electrons are also interacting with each other, and that due to that interaction also there may be some energy, potential energy. So definitely the situation is out of our control as far as one molecule is concerned. But this system of gas may be having billions of molecules, and they are also interacting with each other. So it appears to be impossible to calculate this. U is actually the total energy possessed by the molecules at the molecular level. What is the total energy? This total energy will actually comprise of the kinetic energy of the molecules and the potential energy of the molecules. But you have seen that it is impossible to calculate this. But I would like to emphasize upon here that this internal energy is basically the kinetic energy and the potential energy of the molecules of the system. Okay, as far as finding out the potential energy is concerned in classical physics, potential energy depends only on the separation between the interacting particles. So it doesn't depend upon the frame of reference. So I have no problem with this entity, but definitely I have got some problem with this factor, because this kinetic energy depends upon the frame of reference. So what is the frame of reference? When you plug in the values here, okay, now if I plug in the values here, then this becomes, this was E, so E is equal to this, okay. Now this is E, now what is delta E? Delta E is from here, delta E is delta Ke of center of mass plus delta U. Now if I plug in the value of delta E here, then I'll get an equation. Okay, I'll write the equation also. So if I plug in this value of delta E here, the equation boils down to this. Okay, now this becomes like this. Now if I plug in the value, what is my frame of reference while I measure the value of U? Now that is a big question. This is the question. What is the frame of reference while finding out the value of U? Because U comprises of kinetic energy of the molecules and the potential energy of the molecules, and kinetic energy is frame dependent. So here I would like to emphasize that the measurement of U is made from the center of mass of the system. So while you plug in the value of U here, this should be with respect to the center of mass of the box, which is my system. Okay, now what about delta W on? This is the work done by the external forces on the system. So this will be like, suppose there are some forces acting on the system, external forces, by the surroundings are due to the interaction with the surroundings. Some external forces are have to be considered, because this system might be interacting with the surrounding due to there might be some force interaction. So this work done will be the work done by the, Okay, external forces. These are the work done by the external forces, which is not including the gravitational force, because see, the gravitational force is also an external force here, because we are putting Earth as a whole outside the system. Earth is outside the system. So this will be work done by the external forces other than the gravity force, plus the work done by the gravity force, plus delta Q equal to delta KE, center of mass, plus delta E. Okay, now this is my equation. With this work done by the gravitational force. Now, depends if I say that this is, if I say that this entire thing is my system, because the choice of the system is my discretion. Suppose I say that this entire thing is my system, including the Earth, then this will become, work done by the gravitational force will be equal to minus of work done by the gravity. What is work done by the gravitational force? Suppose I am moving the box a little bit upward. So suppose the center of mass is moving up in the vertical direction by a distance h, then the work done by the gravitational force will be equal to minus mgh. Here m is the total mass of the system, minus because the gravitational force is acting in the downward direction, and we are assuming that the box is moving in the upward direction. So it will be something like this. Now if I include this entire thing as my system, and then this might go to the right hand side, then it will appear like mgh, that is the plus mgh, and that will appear like the gain in the potential energy, gravitational potential energy of the box. So these are the finer nuances of the law, how to apply the law. And there is sign convention also. Sign convention is like this: if I plug in the value and delta W on this vector turns out to be positive, then this means that work is being done on the system. Okay, and if it turns out to be negative, this means that the work is done by the system on the surroundings. If delta Q positive means the heat is entering the system, and delta Q negative means the system is liberating heat, so heat is being rejected by the system. Okay, fine friends, that is all, because I wanted to give this idea of first law of thermodynamics, brief idea, and I believe that these theoretical concepts which I covered today are quite essential in order to apply the laws and in order to analyze situations. Because in the laws I had told you the basic assumptions or the very basic aspects of the law, but as we grow up and we start applying the laws, we'll become more comfortable with the laws. Thank you very much for today. We'll meet tomorrow, and thanks for bearing with me. Thank you very much, friends. Bye.